Hello boys and girls, Brad the Guitarologist here. In this video we're going to take a look at this Lewis electric amplifier that I've had on the channel one or two times in the past. I'll put links up in the upper right hand corner there that you can click on, or down in the description that you can check out the original videos for this. This is the one, if you'll recall, that was painted red on the inside, and I kind of raised a big stink about it at the time because that's kind of a big no-no to paint everything so that a future tech can't see what all the values are of the stuff inside your amplifiers. At any rate, this thing came back because it was blowing fuses yet again. So this customer said that he, pretty much as soon as he got it back, the second or third time he powered it on, it blew a fuse, and then he just didn't call me back or forgot to call me and make me aware of it. So it took a while for him to bring the thing back to me, and then it took a while for me to turn it around too. But I had no intention, first of all, of making a video of this, but I changed my mind. I made a little video toward the end of my repairs on this and diagnosis of the problem for his sake, because I wanted him to understand his amplifier a little bit better, and also I wanted to make it a refresher for me if this thing ever came back, so that I would know exactly what I had done to it. But I also think that this might be instructive for some of you guys who are into cloning old amplifiers or modifying old amplifiers, because sometimes if you straight up clone an old amplifier, you might be missing some opportunities to improve that amplifier. And this is a really good case in point of how some of these old designs might be improved if we just took a little bit of time and thought. So this is a really based off of an old Fender circuit. Like, it's kind of like a twin amp sort of thing from the late 50s. What this is going to show you, it's going to show you the reasons why standby switches really should not be designed into modern amplifiers anymore. This idea of a standby switch, it really does more destruction to the amplifier than it does help the amplifier. And I will go into more detail about explaining that in this video, and talking a little bit about the controversies of the pros and cons of standby switches, and why I don't think standby switches are even necessary in amplifiers at all. Also, we'll talk a little bit about something that you can do to your amplifier designs to ensure that you don't get a huge inrush current that's going to damage some of the components of your amplifier, particularly your rectifier valves, power capacitors, and also your output tubes to some extent, and even your transformers. You can save those by adding this one component, and I will show you what that is and talk a little bit about how to select one in this video. So if that sounds like something you'd be interested in, please stick around. Alright, chap. Hey man, this is just a quick video for your benefit and possibly mine in the future too. I just wanted to show what was going on with this amp. I went ahead and replaced the capacitors. I put some F&Ts in here. This thing had two 22 microfarad capacitors in parallel right here, one here and one here. I replaced the two of those with just one 30 microfarad capacitor. What that's going to do is that's going to ensure that when you take this thing off of standby, that you don't have as large of an inrush current, because there isn't as much capacitance to fill up as quickly. So instead of, like, 44 or so microfarad in total on that first node, we're now down to 30 microfarad, which should be fine. And actually that's more in keeping with the GZ34 book specs as well. Also, we're at 27 milliamps on the plate current for the output tubes, and we just had those disappear. We got 437 volts. I'm going to show you what happens when I, well, first of all, let me show you what that calculates to. So it's 437 volts times 27 milliamps is 0.027. We'll go ahead and put the 1 in there. So that's about 12 watts of plate dissipation, which is about 50% for an EL34. And I think that's probably where I would like to be on this, considering all the problems that we've had, for one. And second, considering the expense of new tubes now as they have increased in price. I would much rather you run this thing a little bit cool than a little bit hot, because you're just going to save yourself tubes in the long run. I did go ahead and replace this 5AR4 GZ34 rectifier again. I put a groove tubes in it, so I've just traded it out with this groove tubes, and the groove tube seems to be holding up much better. I was actually able to reproduce the problem since doing the capacitor swap. So I'm thinking maybe I just got a bad batch of these these 5AR4s. You know, that's a possibility. So I can't say for sure, but that's my guess for the moment, that I might have gotten into a bad batch and just had a brand new tube that was bad. Possible. I did go ahead and modify the power section of this amp too. The power section of this amp was going to a switch right here for the ground. I have deleted the ground switch, so I took the ground capacitor out, deleted the switch altogether. This amp doesn't need a ground switch, dude. As long as you have wiring in your house or wherever you're going to play this thing, that's okay. You should never need a ground switch in a modern amplifier, because you're grounded here. You just simply shouldn't need it. So you have a 3-prong cord. That's why you have that. So we're coming in with the hot lead, and he had the hot lead going here and then bouncing over to the sleeve, which is wrong on this fuse. I went ahead and took it to the tip, so it's a little safer. Also coming out of the tip, we're going now through a CL70 thermistor. What that thermistor is going to do in series on the primary side of the transformer is it's going to slow down the rate at which this amp warms up. So hopefully, if you flip this thing on, like if you were to flip it completely off and off of standby as well, and just flip both of those at the same time, this will slow down the rate at which the amp heats up. Now that's really important when you've got solid state rectifiers. This is not a solid state rectifier, but the GZ34 does heat up quicker than like a 5U4. Which some of the amps that this amp is modeled after on the power section contained back in the day. So just as an added precaution, I've added one here, thermistor. I'm also going to come over here after the, I've decided I want to do this too, I think. Come over here after the standby switch, and we're going to remove the wire that's coming from the standby switch that's going to the rest of the amp, to the first node of the power section, and I want to move that wire over to here. There's an empty terminal down here on this terminal strip. I'm going to move that wire over to there, and then I'm going to take another thermistor from here to here. So when you flip on the standby, or when you take it off of standby, however you want to look at it, but whenever this switch is closed and you've got voltage over here on the other side and you're drawing current, that thermistor will prevent an instantaneous, like on-off kind of a flood of inrush current there. So until this thing reaches working temperature, it's not going to permit all of the current to flow through it. So that's the purpose of this. I'm going to put one on the primary side. I've already done that. And I'm going to come over here after the standby switch, and I'm going to put another thermistor after the standby switch to ensure, like, once again, that this thing does not have that inrush current. So a couple things we've done to prevent the inrush current from being so high. Again, I've changed this from 44 microfarads in total down to 30 on that first node. Also, downstream, these were 30 microfarads. And that's really more than this amp would require, in my opinion. So I changed those down to 22. So in total, we've got less filtering. And in theory, you would think that would mean more noise, but not necessarily. I think in this case what it's going to mean is less inrush current and less of a chance that this thing is going to keep popping fuses like it was doing. And right now with the new rectifier and with all these other provisions that I've done, and again, I still have not put the thermistor in yet. We'll do that in just a second. I've gotten this thing to where I think it's not going to pop any more fuses, but watch the current figure right here. It does spike up, but not as high as it was doing before. Before it was spiking, what, like 3 amps or so, and it was blowing the fuse. But now if I turn off the standby, you'll see the current goes down to about 0.44 amps. And if I take it back off of standby, I'm going to take it off here in a second once the voltages crash all the way down. You'll see it spike, but it won't be nearly as high as it has been in the past. See, it was 1.3 amps, which is safe. That's not a problem. But you can see what using the standby switch does to an amp. You know, and this is the big debate over standby switches. That, you know, oh, they're there to prevent cathode stripping, but that is not a concern. From all of my reading, cathode stripping is something that is not a concern unless you have a super high, unless you have tubes that you're dealing with which are super high frequency or super high, what am I trying to say, super high plate currents. That's not a concern. So and in tube amplifiers for guitar, that's never going to be a concern. I would just advise you to completely ignore the standby switch as if it wasn't there. Leave it on all the time and only use the on-off switch, and only turn it, like if you're going to turn the amp off, you can turn it off with the off switch. But wait for just a minute or two until the tubes cool off before you turn it straight back on. Now that's not going to be ideal if you're in a gig situation necessarily, but it's going to prevent you from coming back from a break and finding out that your amp blew a fuse. You know, I would much rather have to do that, wait for it to warm up just a couple seconds, than, you know, have to worry about blowing fuses all the time. You see the voltages have gone down about as far as they're gonna. I'm gonna go ahead and turn the amp back on now. It will take a second for this because these tubes do cool off a little bit, not too quickly, but it will cool off. Then you've got the thermistor also, which has to cool off, and the thermistor will prevent inrush current, and the rectifier will also on the secondary prevent some of that current. But we're going to go ahead and take it directly off. We're going to turn it on immediately. So here we go. In 3, 2, and again we're going to look at current up here. In 3, 2, 1. You can see that did not spike really at all. And just for giggles, I'm going to let it warm up. Go ahead and let it warm up. We'll let the power tubes go ahead and get up to about their operating plate currents, which is what I say, about 26 or 27 earlier. That's probably enough. So what I'm going to do is I'm going to shut it off and then right back on, and we'll see what the current spikes at. I saw 2 amps there. But I did not see any shorts or lightning in the GZ34 rectifier or anything like that time when we didn't pop a fuse. Let's do it again. That went up to 3 amps. Or did you see it? It did go up to 3 amps, but the amp didn't blow the fuse. But see, it's not good. It's not good to do amps like that. And if I did not have that thermistor in there, it probably would have blown that fuse just then. The thermistor is probably all that saved it. So I don't know, man. I just would be very careful with this amp. There's a huge inrush current with this amp, with the way it's designed, with the power transformer that's in here. you know, I don't know what this power transformer is or where he got it or what the exact specs on it are. You know, I would assume that it's made for this purpose, but I just don't know. You know what I'm saying? So I would just be very careful turning this thing off and on again really quickly. And also, since you said, you know, you were jamming on this thing when it happened the last time you blew a fuse, and you had reached back here and moved this around, you know, I don't think it has anything to do with it, but I do notice that when I'm turning this knob down here a little bit, you know, it does jump a little bit on the milliamps, but it shouldn't be enough to see how it goes from 72 to 73. That shouldn't have been enough to do anything to it. So I don't know. I think it was just a corollary and not a cause. But right now, man, this thing is doing what it's supposed to do. It's just sitting here idling. It's, you know, like I said, I've turned it off and on several times. I am going to jam through it as well just to make sure. Got a new toy here. Let's see. Let's look at the waveform. All right, see, we're getting good waveform here. There's 81 milliamps at 384 volts. See, that's like 31 watts right there. So I mean, you got to be very careful, especially if you're using like an attenuator. Just be careful. Don't crank your master volume too much. Okay, so I've got the preamp cranked. It's all the way cranked. Okay, here's our waveform, and there is our plate current. There's our plate voltage. Now watch this. Watch the plate current when I turn this knob when I've got a signal going through it. You see how the plate current jumped? Pretty massively, actually. That's a pretty big percentage, from 36 up to 50 just from turning that knob all the way one direction. I may go ahead and bias these tubes a little colder as well, as you know, just to get you out of the realm of danger here. Hang on. All right, I'm gonna crank that. Okay. Okay, with as hot as you like to apparently run this amp, I'm going to bias you a lot colder. I think I've decided that's the best way to go forward here, and that's going to prevent you from popping something in the future. Let's go ahead and put it back to idle. All right, so we're at 456 times, there's 13 milliamps. That's 6 watts of plate dissipation per output tube at idle. I'm going to jam around on it like this for a little bit. I'm going to plug it into an actual speaker and jam around on it and just see what it's sounding like when I crank. And because I suspect that you're cranking this amp. You know, I suspect you're a rock and roll dude and you crank this amp, and there's nothing wrong with that. You should be able to crank your amp without fear. So, but I'm going to bias it with that in mind. So, I mean, you can correct me later if I'm wrong, and I'll always rebias this thing for free for you. I don't care. But I just want to make it where it doesn't keep doing this to you, where it's popping fuses and everything. As a matter of fact, I'm going to go ahead and shut her down. I'm going to put the second thermistor in, and that should help a little bit further too. And then we're going to come back and assess where we are with it. Okay, after a little bit more messing with this this Lewis electric amplifier, I think I've gotten everything where it needs to be now. 34.4 milliamps of plate current is what we're measuring here right now. 422 plate volts. Can't really see it, but there's 0.83 amps at idle. We're gonna put some signal through it here. You can check out what it's doing on the scope. So we're going to set this to a sweet spot here. So we're going up to about the time it starts distorting on the preamp. And you can kind of see the waveform here. It's kind of wavy. Okay, so that's on the first stage there. And now we're going to just send it over the top with this, and we'll get it to the point where it's compressing pretty good. And you can see the, let's get that about like that. And then the crossover, once it distorts here, let's get that down where you can see it better. Okay, you can see the compression here. You see the crossover distortion is not really severe, but there is a little bit of a notch right there. But it's not too severe. It's just pretty good. And that looks like that's a sweet spot to me at about 9 and 9 on both of the volumes. I bet if you were rocking that right there, 9 and 9, I've got the treble pretty cranked, but back off that a little bit. Even probably even set the boost the mids a little bit. Got the presence boosted up to about 10 or so. Yeah, mid-range about 10. But you can see what it looks like there. Nice and compressed. It's chopped off at the top. The tubes are pretty nice and matched. You can see they're reaching about the same level on both sides, and they're clipping about the same time. So top and bottom. So we don't have a big mismatch of tubes. These tubes are really well matched. That looks fucking fantastic. And again, if we look at everything at idle, 34 point, well, we might as well say 35 milliamps there. So 0.0356 times 425 volts. That's 15 watts of plate dissipation. That's about 60% of the 25 watts maximum for an EL34. So we're good on that. The other thing that I did was I came in here and I put a second thermistor in here where I said I was gonna. So there's the second thermistor right there. So here's thermistor number 1 over here on the primary. So that's basically keeping the inrush. That's keeping the inrush at a minimum on the primary side. And then when you open up the standby switch, this thermistor is right after the standby switch. And what that does, it basically, well, you'll be able to see it actually. I'll show you exactly what it does. So if I take my probes, we're going to let it cool down for just a second. I'm going to take my probes for my meter. I'm going to leave it on volts so that we can see the voltage drop across this thermistor. So I'm going to hook it on the other side here if I can get a good place to hook it. I think that's there. So let's try it. So when I turn this, when I first flip this switch, I'll say when I flipped it. So right now we're at 0 volts drop across that thermistor. Now when I flip the switch, watch, you're going to see about maybe 1 point or 2 point something volts at the very beginning, right after I switch, and then you'll quickly see that start to drop off to less than 1 volt of voltage drop. So what that's doing is it's giving a higher resistance in the beginning. So the inrush, during the inrush current, there is a higher resistance. So it's going to take up more of the total watts. It's going to dissipate some wattage, saving some of the components downstream. So here we go. In 5, 4, 3, 2, 1, now. You see it went to about 1.9 volts in the very beginning there, and then it kind of dropped off, and now it will continue to kind of slowly drop off. But the initial wave of current that comes in, that inrush of current, is what we're really concerned with. So if I flip that off again, goes back down to 0, flip it back on. See, it didn't go quite as high that time. It got to about 1.3 volts, but that's because it was still probably a little bit warm. But that's what the thermistors are doing. They're preventing the inrush of current. So I've got 2 of those in here. Again, I just basically rewired the primary of the power section because it was kind of just wrong, really, for modern amps. You don't need a ground switch. The ground switch is out of this. Changed all of the capacitors, put FNTs in here, good capacitors, changed some of the values. I think this amp is ready to rock, so hopefully this will never do what it did again. It was having problems for sure with that that other GZ34 that was in here. It was arcing internally, and this Groove Tubes has not done that a single time. It gives us an idea for the future, if this amp ever comes back again, of what's been done. Alright guys, that'll do it for this video. I hope you've enjoyed it. It was necessary for me to remember what I've done here. So if you liked it, hit subscribe, and for now, we'll see y'all later.